So my name is Krishna, and I've been working for VMware for quite some time, and I'm in the performance engineering group, and I focus on core platform performance, which includes the CPU scheduler, virtual machine monitor, and I also use esxtop on a daily basis. So my talk here is basically based on my personal experiences with using esxtop for doing troubleshooting. And I want to demonstrate how to use esxtop for various scenarios and how to look at the counters, how to make sense out of these counters, how to correlate these counters from different statistics, and how to make sense out of it. So that's going to be the theme of the talk today. So before we go deep dive into esxtop, I actually want to talk about a few other performance management tools that we have, just to give you a bird's eye view of what all things are there apart from esxtop. The first thing is a very basic tool. It's vCenter alarms. It basically relies on static thresholds. Like, for instance, you can say, throw me an alarm if a CPU usage exceeds 70% or 80%. Then it sends you an alert, and you get notified. This is a nice tool if you want to get alarm notifications for specific events that you know will cause a performance degradation in your environment. But it's not a clear indication that you actually are seeing a performance problem just because an alarm is triggered. And then we recently acquired a company. It's called Integrion, and we renamed the product as called vCenter Operations. Now, this is a product which uses dynamic thresholds, and it uses dynamic thresholds based on analytics. So basically, it observes your performance counters from your entire data center. It collects them for 2 or 3 weeks, and it remembers, like, what is the normal pattern that I see during a particular day, a particular time. And then if that normal pattern changes, let's say in the next week, then it triggers an alarm. So it uses something called as dynamic thresholds. There's a lot more complex things goes into this tool. I highly recommend you guys to check this out, either at the booth or there's a separate talk on that. And then vCenter charts, which we've been shipping for quite some time. The nice thing about vCenter charts is it gives you a historical trend. So you can actually look how your CPU usage was there, like a few days back, a few weeks back, a few months back. It's also useful for doing a post-mortem analysis. For instance, a problem happened and it went away. Now, you can't run esxtop on the box to do troubleshooting, so now you can go back and look at the vCenter charts, and then you can compare the performance metrics, and then you can do troubleshooting. And, of course, esxtop, which is what I'm going to talk about in this. And the esxtop primarily is designed for live troubleshooting, and it's meant for doing root cause analysis. It's not meant for performance management tasks or performance reporting and for those kind of use cases, even though I know a lot of you people use esxtop for that. esxtop is meant for live troubleshooting, but you can also do offline troubleshooting by saving the data of esxtop in a CSV file, and then you can use tools like esxplot or perfmon, or you can write your own custom scripts to do post-processing. For really complicated problems, the technical support may ask you to get a performance snapshot, and so that they can do offline analysis if they can't log into your ESX box to run esxtop. And previously, we used to ask this command in a command line. You have to log into the machine, run a command called VM support with some flags in it to collect the performance snapshot. Now we have a GUI tool. This is part of ESX 5.0, so you can actually collect performance snapshots from the GUI itself. Okay, so with that said, this talk is going to focus mostly on esxtop counters, and the emphasis here is on the counters, not the tool itself. Whatever you learn from this counters, you can basically apply for any statistics that you collect through vCenter or any other tool. I'm just going to explain how the counters work and how we can use these counters. There is this document called esxtop manual, which covers the basics of the product, which I'm not going to talk about in this session. There is a document we maintain which goes into the detail of how the statistics themselves are collected and what's the meaning of the statistics and those kind of details. And this is also something that I'm not going to cover in this talk. And I've done previous VMworld talks, which talks about esxtop in different scenarios. And I've spoken about a number of scenarios in the previous talks, and I'm not going to talk about those as well in this. So what am I going to talk about? Well, before we jump into that, this is a very basic introduction to esxtop, like a quick 10-second introduction to esxtop. So esxtop is a tool which has many screens like CPU, memory network, disk adapter, and then we have 3 different screens for storage-related statistics. We also have a screen for power management-related statistics. So basically, you switch between those screens by pressing these keystrokes like C, M, N, D, U, and V, and so on. And each of this basically exposes your basic underlying functionality of ESX. By looking at these counters, you can actually understand what's going on in the box, how your system is behaving. So, before I dive in, let me want to quickly walk through the new counters we introduced in ESX 5.0. I'm not talking about any of the counters which is added in the past, just new counters which is added in 5.0. So the first, when you launch the CPU screen, it might look pretty much the same compared to the previous versions of ESX. You may not see any big difference, but we just added one nice little information there. Now we show the number of VMs that you're running on the box, and also what's the total number of vCPUs that you're using on the box. So this gives you a quick summary. And this is pretty useful if you want to know if you're overcommitting what is your CPU overcommitment ratios. Let's say you have 16-core machine, and if you see 32 vCPUs, then your ratio is 2:1. So you get a quick glance, you get a quick idea. And this also gives you an indication how many virtual SMP VMs you might have, because we also show the VM count. All right. The next one is a very simple counter. It's called VMweight, but it has very interesting use cases. I'm going to talk about that later. But basically, this counter is it's a derived counter. It basically subtracts the value of idle time from the wait time and then shows it as VM wait. I'm going to talk about this later, so I'm going to skip the actual details now. And then in the power screen, this is a screen that we added in ESX 4.1 where we show the processor P states. So let me explain what P states are. So P states are basically different clock frequency a processor can step into. So this is for people who are familiar with Intel speed step for the laptop processors. They have the same stuff for the server class processors now. So that's called Intel P states. What we now show is we also show the CPU frequency in different P states. So in the screenshot, you see that you have P0, P1, P2, and P3. So you have 4 P states. And we also show what's the clock frequency. So P0 is your rated clock frequency. That's your processor maximum frequency that it can go. It's 2.4 gigahertz. And can step all the way down to 800 megahertz. So this P states will vary quite differently depending upon which processor model, exact model number that you have. Different processors, some processors are designed to have more P states, some will have less number of P states. The P states will be visible only if you set the power management setting in the BIOS to be OS controlled. Basically, this means the BIOS will expose the processor P states to the operating system, and only then we can show this information. So I'm going to talk about this in detail in the latest slides. So let's move on. There's another counter that we added. It's called, it starts with F commands per second, F reads per second. This is in the disk adapter screen. What this counter shows is the number of IOs which failed with your storage array. Now previously, both successful IOs and failed IOs were accumulated in commands per second, SCSI commands per second. And there's no way to distinguish whether IO actually failed or not. Now we keep those stats separately. So this will be useful if you're tracking any storage-related problems. You can see if your IOs are getting failed. So we also have, even though I haven't highlighted here, I just want to point out, there is aborts and resets. These are also SCSI error commands. But they kick in much later. You would see the failed commands happening first before you see the aborts and resets. So that's something to keep in mind. Okay, and then we have this new counters added in the LUN screen. It's called VAI. For people who are not familiar with VAI, it's the vStorage API for array integration. Basically, what this means is your ESX server can send special SCSI commands to your storage array and offload the operations to the storage instead of it doing all the I/O. For instance, if it wants to write zeros for a 10 gig block, instead of writing zeros for the entire 10 gig block from the ESX, it can go and tell the array, write 10 gig block from this block number to this block number, and the array will do it in the backend. So this basically saves I/O traffic on your fiber channel adapter. So this is pretty cool. We had a lot of counters in the previous version, so we just added one additional counter, which is very relevant for people who do thin provisioning. So when you do thin provisioning, we expand the virtual machine disk file on the fly, but you may also delete some content later. And when the content gets deleted, now we can notify the array saying, you know what, I deleted this block, so you can go and free it up in the backend. So that's what this counter tracks. Then there's a new feature which we added in ESX 5.0. It's called as low latency swap. In the UI, you would see it as host cache. What this feature does is, if you have SSD drives, local SSD drives in the ESX box, we now use the local SSD drives as one other medium for swapping instead of using your VMFS volume for swapping, instead of using your SAN LAN for swapping. So we can use both the SAN LAN as well as your SSD drives. Now, SSD drives typically don't come in big sizes, right? It comes as small sizes like 256 gig, but you might have a lot more VMs. So we have a policy which manages how to effectively use that smaller disk space that you have on the SSD drives. This is a feature we introduced. This actually improves performance quite a bit in memory overcommitted scenarios. Compared to swapping to a regular LUN, swapping to SSD makes a humongous difference in performance. So now we have a counter which actually specifically tracks what is the swapping activity on this particular SSD drive. So that's what this counter does. So you see swapping read and write activity to this one. But just one embarrassing caveat, this counter is broken in 5.0. The version is released. So there's a bug file for it. It should be fixed in some update release. But fortunately, we also expose this counter in the vCenter UI. And those counters they're working fine. So now you can get those stats from the vCenter UI. All right, so before we go into troubleshooting scenarios, I want to get the basics correct because there's a lot of confusion on CPU metrics, especially with the introduction of power management. So next few slides, I'm going to talk about the CPU counters. So let's say this is elapsed time. The elapsed time could be whatever your observation period is. So a typical observation period for esxtop is 5 seconds. So that's this entire elapsed time. Now this time can be broken down into several different states. The first which is wait time. Wait time basically means that whatever that you're observing is actually not using CPU, it's just waiting. It's doing nothing. Or it may want to run, but is not able to run because it's in a ready state. So that's the other component. There's a third component which is called co-stop, which is very similar to ready time, but co-stop basically means you are forced to deschedule because your sibling vCPU for an SMP VM has made a lot of progress and you want to catch up with your sibling vCPU. So we forcibly deschedule you so that you can catch up with your sibling vCPU. So that's the co-stop state. So co-stop and ready are kind of very similar. Basically, you're forcibly descheduled. Well, co-stop is forcible descheduling. Ready time may or may not be forcibly descheduled. I'll talk about that a little later. And the last portion is the runtime. So runtime is the actual time your VM actually spent running on the CPU. That's the time which basically uses the CPU. Now, this wait time can be broken down into idle time. What this means is the time I was waiting, I was completely idle. I had nothing to do. So this counter is actually tracked only for vCPUs. It's not tracked for anything else which is running on ESX. It makes no sense for anything else. It matters only for vCPUs. And then there is a counter called swap wait, which basically says that I'm waiting because I'm swapping right now. My VM cannot make progress because you're swapping. You're reading something from the disk, so we actually stun the VM The VM cannot run until you read everything from the swap file, and then you can make progress. So that is the swap wait time. Then there is the remaining portion of the wait time is the block time. We don't have a separate counter for it, but it's an important time to remember. So I'm going to talk about that later. That's why I mentioned that it's blocked. All of the counters which are highlighted as bold, in bold letters, they are basically available in esxtop. The italics ones are not available. But you can derive it. Basically, if you want to know the block time, you basically subtract wait minus idle minus swap wait. That's your block time. Now, the idle time of a vCPU actually includes the guest I/O wait time. Your guest could be idle because it's idle. It has got nothing to do. Or it basically issued an I/O, and it's waiting for the I/O to come back. And until then, it can't do anything. It can't make any progress. So it's the guest I/O wait. So this is something to remember, because the wait time in ESX is very different from the I/O wait that you see from within the guest. The I/O wait which is seen in the guest actually gets accounted as idle time on the host. Then the VM wait counter, which I briefly talked about, as a new counter which is introduced in ESX 5.0, basically is a combination of the swap wait time and the block time. So that's what the VM wait is. Now the ready time, you can accumulate ready time for two reasons. One, basically you are contending CPU with other VMs on the box, or the scheduler is forcibly descheduling you because you're exceeding your quota. Now we can set quota basically by setting limits, resource limits. So you can say this VM gets the maximum CPU of 2.4 gigahertz, but your clock frequency on the box could be 2.8 gigahertz. Now, if the VM wants to run all the time at 100% utilization, since you set a resource limit, we will forcibly deschedule the VM so that it only gets to use a 2.4 gigahertz cycles. So in those cases, you are max limited. You are limited by your resource limit max settings. So that is tracked separately from the ready time. So if you want to know the true CPU contention that is happening with other VMs, you basically have to subtract the ready time from the max limited time. All right, so with that said, so in this whole thing, the only time when you're actually using CPU is the run portion, the right-hand portion. It's a very small portion that are in the screen. That's the time you're actually using the CPU, right? So you might think, oh, so my run time should be my CPU usage time, right? But it's not that simple. Okay, so used is in our ESX terminology, use time is basically the CPU charged time for that particular VM. So we charge CPU cycles for the VM. It's a chargeback policy. So how it works. So if you're using all of your runtime, yes, used is run. But we also might do some system level operations for your VM. We'll process interrupts. We can do some activity. The VM kernel can do some activity on behalf of a particular VM. So those CPU cycles could happen on a different CPU than where your VM is running. So they could happen in parallel. That's why there are two different lines, because I'm showing they're happening in parallel. So in those cases, the system time actually has to be charged back to the VM's CPU usage. So use is now run plus sys. I'll give you an example for this one later in the slides. Okay, so that's not it. There's also a component called as overlap. So overlap is a component where a vCPU is running, and then suddenly the vCPU got interrupted because you have to service an interrupt, or you have to do some of the low-level system work. And then you resume the activity, and then the vCPU finishes running, right? So that time is an overlap time. And that system activity can be either for your VM, or it could be for a different VM. So that usage has to be subtracted from the runtime. So used is basically run plus sys plus overlap. So this is all internal gory details. You really don't have to worry about it. Ultimately, what you need to worry about is the use time. So what this means is this equation basically tells you one thing. Your use time could be greater than 100 because you are adding system time to the used. So don't assume that used has to be capped at 100. Used here is the charge back to the VM, which could be greater than 100 even for a single vCPU VM. But used also could be less than run if your CPU is not running at its later clock frequency. This gets really complicated here, so I'm going to explain this in another slide. Impact of P states. So we talked about these P states briefly. So I said there are 4 P states. The highest clock frequency this machine supports is 2.4 gigahertz, and you can step it down all the way to 800 megahertz. Now there are 2 counters here, used and util. So to simplify things, I've given this simple hint here, which kind of simplifies this, but internally it's calculated in a difficult to understand way, so I kind of simplified it here. Used is basically CPU usage with reference to the base clock frequency. So which means if your clock frequency is 2.4 gigahertz, and if you're using the entire 2.4 gigahertz, your usage is 100. But let's say you're 2.4 gigahertz, and you're using 3 gigahertz because you're also using another CPU, part of another CPU for a VM, then it will be greater than 100. Util, on the other hand, is referent to the current clock frequency. So if your current clock frequency is 800 megahertz, and you're using 800 megahertz, then utilization would be 100. But used would be much less. So this table basically gives you that information. So P0 state, which is your standard clock frequency state, percentage run is the time that you spent on the CPU. So if you're spending all the time, 100% of the time on the CPU, your util is 100 and used is 100. But let's say you take the P3 state, you're spending all the time on the CPU, but the CPU is running at a much lower clock frequency, and therefore the usage is actually much less. You would only see 33%, but your utilization could be 100%. So I was talking to a customer during a group discussion, and somebody was saying that sometimes they notice a difference in CPU utilization between the guest OS, what the guest OS reports, and what the host OS, what the esxtop reports. For example, the guest can say CPU utilization is 100%, but you go to esxtop, it might show the CPU utilization is, CPU usage is 33%. That could happen for a reason here. Like, for example, you're running in the lowest P states because you have power management enabled. Then the guest thinks it might running it all the time, which is true. It's running it all the time, but you're only using a small portion of the processor capacity. So that's what usage is about. So this is very important to understand because a lot of people get confused the difference between used and util. All right, so to summarize this, the factors that affect VM CPU usage accounting are the following. You have a chargeback, which is a system time, which I stated. You can also have usage vary because you have CPU frequency scaling. There's one thing I didn't mention about is called turbo boost. So I mentioned that the CPU frequency can step down from 2.4 gigahertz to 800 megahertz, but it can also step up in some cases, and that's called turbo boost. That functionality exists in Intel and ALM processors and on all the latest Intel processors. So when turbo boost kicks in, your use can be greater than run minus sys. So it's something to keep in mind. I'll actually show you a screenshot where you can actually identify this. Of course, power management I talked about. The third component which can affect CPU usage accounting is hyperthreading. And I'm going to talk about that in the next coming slides. Okay, so first let's take an example how to spot poor performance because you have power management enabled. And because the power management is enabled, your processor is running at a lower frequency, and therefore you're experiencing a performance problem. So if you look at the screenshot here, everything looks nice and dandy, right? Yeah, the VM is using 70% CPU cycles. You don't see any ready time. Everything seems fine, right? But there's a catch point here. There's a difference between the run time and the use time. So if you remember, runtime is the time that you spend occupying the CPU. So you are occupying the CPU all the time, but your usage was only 74%, right? So what's going on in this case? In this case, the VM is using only 75% of the clock frequency, and the reason for this was, in this case, was I enabled power savings in the BIOS. So if you enable BIOS-based power savings, BIOS can automatically put your clock frequency to the lowest clock frequency possible so that you save power. And this works transparently. We wouldn't even know whether the BIOS is controlling the clock frequency. But you can notice the artifacts by looking at these counters. All right. The other case is specific to hyperthreading. So this is an example what I'm talking about where you're sharing two logical CPUs of the same physical core, and what will be the performance impact in that case. So this is what I'm talking about. So I just want to give a little bit of terminology here. We have PCPUs. PCPUs includes logical CPUs, even though it's called physical CPUs. And there's also a concept called as core, which is the absolute core, which is the physical core that you have. So when you have hyperthreading enabled, you basically have double the number of PCPUs than the cores that you have because they are two logical CPUs. So in this case, if you're running two VMs, the two VMs can be placed on two different PCPUs, right? But with hyperthreading enabled, you have more options. You have 4 PCPUs, and you can place a VM in any of those 4 PCPUs. By default, the ESX scheduler tries to put these VMs on physical PCPUs of different cores so that you don't share the same underlying core. This is to help you in performance. That's a default behavior. But if you set CPU affinity, and you set CPU affinity for 2 VMs to be CPU 0 and CPU 1, the case on the left side, when HT is off, they'll be running on different physical cores. But when HT is enabled, you would be running them on the same physical core. So that's one pathological case that you can hit. Even though ESX tries to avoid them scheduling on the same core as much as possible, as you add more and more VMs, it may not always be possible for us to schedule them on a separate core. So there will be some sort of core sharing will happen, which should be fine. But we can actually spot this activity by looking at the esxtop counters. So this is a case where there is no core sharing happening. So how do you track this? Is there are 2 VMs running. Both are running CPU usage like more than 100%. I said that it's possible to get more than 100% because you can have system time. In this case, it was more than 100% because turbo boost was kicking in. Because if you look at the system time is 0. The usage is greater than 100 because you're basically using Intel turbo boost. Now, if you see, there is a core util, which basically tells you that you have 2 cores. Actually, you have 4 cores, but I've only highlighted 2. But if you look at the PCPUs, you have 8 PCPUs. So what this tells you is that you have hyperthreading enabled because you have double the number of PCPUs than the cores. So in this case, 2 separate cores are getting used. That's why 2 cores are showing 100%. So there is no core sharing happening in this case. So everything is fine. But, okay, I said turbo boost is also kicking in, so that's an example. But in this case, core sharing happens. So what do you see in this case is you're running 100% of the time. The used is less than 100. So something is going on in this case. And you see there are 2 PCPUs, adjacent PCPUs, both are consuming 100%, and they share the same underlying core. The reason why the used is 60% in this case is that's how we account when you're fully occupying a logical CPU and also sharing the other logical CPU with another VM. Because you're not actually using the full capacity of the processor. If you use one logical CPU and one core exclusively, then you're using the full capacity. But if you're using 2 logical CPUs and sharing the same core, you're not using the full capacity, and therefore our charging mechanism kicks in and charges like 60 or 65% for that particular vCPU, even though it's running at 100% of the time. So this is one way to spot it. There's also another way to spot it. We have a counter called lat_c, which basically tells you what is the CPU latency that you have accumulated due to a CPU-related issue. So in this case, lat_c basically says that this is the amount of CPU time you didn't get because you are doing core sharing. Now, lat_c includes other components also. It includes its ready time. It includes its max limit time. It's actually a cumulative stat. It basically says this is the amount of CPU cycles I didn't get for whatever number of reasons. It might be ready. It could be core sharing. It could be hyperthreading. It could be many number of reasons. But in this case, it was purely due to hyperthreading. All right. The next one is performance impact of swapping. So everybody knows swapping is bad, and you can easily track swapping activity by looking at the swap counters and the swapping rate, right? But how do you estimate what is my performance impact? if I see some swapping, how much of a performance degradation can I expect for my application? Is there a way to identify that? So here an example is there is some swapping activity going on, not a whole lot. You are swapping like 0.06 swap rates per second, which is not a whole lot, right? So in the CPU screen, we have a counter called as swap rate. So before that, so this VM is completely running a CPU-bound workload. And you're seeing the runtime is only 84%. So there are some 16% is missing. You're not using the 100% runtime. You see the idle time of the VM is completely zero. So the VM is constantly running, but your runtime is 84%. So what happened in this case is the VM is waiting on something. The remaining 16% of the time it's waiting. Whenever the VM gets scheduled, it runs. There's no idle time inside the VM, but it's waiting on 16% of the time. And the wait happens because bulk of the time you're waiting because of swapping activity, because the VM wait is completely attributed to the swap wait in this case. So this gives you an estimate that this VM should experience at least a 16% performance degradation. Even though if you look at the swapping rate is extremely small, you could have a 16% performance hit in this case. So this is why swapping is so critical, because when even a small amount of swapping, we have to block the VM completely until the page gets read back. And that wait time could be really long. So in this case, it's like 16% of your time was waiting on that state. Okay, how to identify storage connectivity issues. So usually for connectivity-related issues, it's better to go to the logs, because logs usually will have any kind of storage problems. Like if you lost access to the LUN, you will see that in the logs. But sometimes you can even track this from esxtop. So that's what I'm going to show in this case. So in this case, I have an NFS data store, and I see a lot of activity going on in the NFS data store. I'm doing like 76 megabytes reads per second. Heavy I/O activity is going on in the NFS data store. Now, when I look at the VM, all the activity is coming from the VM, and the VM is consuming like 110% CPU. And if you look at it, 43% of the CPU cycles is getting charged from the system time. And this typically happens for an NFS data store because the VM is doing local I/O to this local disk, and that I/O needs to be translated into an NFS I/O, and that is done by the VM kernel. So VM kernel is now doing some additional I/O on behalf of your VM. So those CPU cycles get charged back to the VM, and that's why you see the system time in this case. That's why it's 43%. So this is all fine. So everything is moving along fine. You're using your NFS. You're seeing some system time. Everything is fine. Now let's take a look at this case where suddenly the I/O activity to the NFS data store stopped. Right? You look at the VM, and you look at the VM CPU usage. It's not at all using any CPU. So how can you tell in this case that the VM has gone idle? The VM is not doing any I/O. Or I really have some issue here. Is there a way to spot it just by looking at these counters? Quite interestingly, you can do that. This VM wait counter actually should be 0 if the VM is completely idle, it's not doing anything, it should be 0. But in this case, it's 74% of the time, which means this VM is blocked. It's not running. And because it's blocked, it's not doing any I/O. And therefore, your CPU usage is low, and that's why you don't see any I/O activity to the NFS data store. So the way I trigger this problem is pretty simple. I basically went and messed up with the networking configuration of my NFS data store while the I/O workload is running, and suddenly the VM CPU usage dropped because we are blocked on the I/O. So I just have to mention this. This blocking doesn't happen all the time. It happens only when you use like thin provision disks, or in some special type of disk formats. In other cases, you may not see this blocking. So I just want to highlight that. So this is a custom created scenario. So you may or may not see this. But I just want to highlight the point of the usefulness of the VM wait counter, which basically gives you an idea whether the VM is blocked for some resources. You can also get this VM wait counter, for instance, if your VM is blocked because you ran out of disk space, which means we'll stun the VM when the VM ran out of disk space in a thin provision case, and then you will see the VM wait counter showing up. Okay, so this example is going to talk about poor performance during a snapshot revert. So this is a counter I never discussed in my previous VMworld talk, so I created a custom scenario to showcase this counter. So there's a counter called checkpoint read and checkpoint target. which is a counter which tracks your suspended snapshot file. So this VM's memory size is 4 gig. That's why the checkpoint target is 4 gig. And I basically suspended the VM and I'm trying to resume it. The checkpoint read tells you how much of my suspended file is getting resumed right now, how much is in memory right now. So if you've read everything in the target, basically everything is in the memory. Otherwise, you're still reading from the disk. So this is useful. Let's say you have a huge VM, let's 32 gig VM, and you suspended it, and you're resuming it, and you're trying to see how long it takes for it to resume. And if you think it takes forever to resume, then you can run esxtop on this and see what's the I/O activity which is happening when you're doing resume. But you shouldn't be looking at this I/O activity from the VM's I/O activity point of view, because the VM is not doing any I/O. The ESX is doing I/O on behalf of the VM. So you won't see any activity if you look at the VM's I/O activity. But if you go to the adapter view, disk screen, you can actually see the disk reads are happening in the background because now we are resuming the VM. So if this disk reads for whatever reason is slow, your snapshot revert operation is going to take a long time to complete, especially for really large VMs. Okay, the other one is Wide-NUMA behavior in ESX50. So Wide-NUMA is a scenario where a VM's memory size or its vCPU count cannot be fitted into a single NUMA node in your box. So that's what we call as Wide-NUMA. Prior to 5.0, we didn't have any support for Wide-NUMA. Basically what that means is if a VM exceeds a NUMA node size, we basically won't do any intelligent NUMA memory placement for those VMs. We would just basically give up our hands and say, memory will come from anywhere. We don't care about whether it's local memory or remote memory. We don't do any optimization. But in starting from 5.0, now we handle Wide-NUMA cases specifically. So this shows the specific example. So here you have 2 NUMA nodes, each NUMA node with 16 gigs of memory. You have a 1 vCPU VM, and that's the only VM which is running in the box. The VM's memory size is 24 gigs. So VM's memory is clearly exceeding one particular NUMA node size. Now, in this case, we assign a home NUMA node of 0. What this means is, as the VM's memory consumption increases, even though the 16 gig is the VRAM size, you may not be using all the 16 gigs. But as its consumption increases, we'll try to fill as much memory as possible in the home NUMA node 0. And then any excess memory from the home NUMA node 0 will overfill to the other NUMA nodes. So that's the behavior in this case. But another example here is that you have 2 16 gig NUMA nodes again. But this time you have an 8 vCPU VM. And this particular box, the number of cores in a particular NUMA node is 4. So here your vCPUs are exceeding the NUMA nodes. And your memory is also exceeding the NUMA node because it's 24 gigs. So in this case, if you notice, we assign 2 NUMA nodes for a VM. So this is a very special case. This is a new feature we added. So what this means is we'll split the VM memory into 2 sub-NUMA nodes. And part of it will come from NUMA node 0, and part of it will come from NUMA node 1. And we also expose this NUMA node settings to the guest. And that we call as the virtual NUMA. So this will kick in only when your vCPU count is like 8 vCPUs or above, and you're exceeding the 1 NUMA node core size. So this is a new feature. This is something you can observe in the esxtop. Okay, the other one is network packet drops due to CPU saturation. Of course, networking side, I want to highlight one thing, which is you can have packet drops at the virtual switch layer, and you can also have packet drops at the physical switch layer. You can also have packet drops at the physical NIC layer. You can also have packet drops at the guest OS layer. What esxtop shows is only packet drops happening at the virtual switch layer. If a packet gets dropped in a physical switch, you're not going to even see those packets. If a packet gets dropped in the physical NIC, you're not going to see it in the esxtop, but you will see it in the NIC statistics. So you can run ETH tool command on the ESX command line, and you can look at the IO statistics, and that will show it. If a packet gets dropped in the guest, we wouldn't know it, because we pass the packets to the guest decides to drop it for whatever reason, we wouldn't know it. So that's something to remember here. This is only packet dropped at the virtual switch. So here, I'm seeing like 753 megabits network traffic. It's on virtual switch 0. and it's happening on VM NIC 0. That's the NIC which is sending that much traffic. But I have two VMs. Only one VM is doing I/O activity, and that VM is seeing only 436 megabits network traffic, and it's the same VM NIC 0. So this shows you some disparity, right? VM NIC 0 is getting 753 megabits traffic, but your VM is only getting 436. So something is going on here. So what happens in this case is this VM Ubuntu 6.4.5 was dropping 42% of its packets. Okay, the next question you need to know is why it is dropping packets. Why would the VM suddenly decide to not accept those packets? So packet drops happens if the guest is not consuming those packets. When the guest is not consuming the packet gets queued up, and then you have a fixed queue buffer, and then after that the packets will be dropped by the virtual switch. So in this case, the Ubuntu 6.4.5 VM is consuming a lot of CPU, which is not a problem, but it also accumulates a lot of ready time. So what this means is the VM is not running, and if it's for like 100% of the time it's not running, it's a 2 vCPU VM, 100% of the time it's not running. So since it's not running as frequently, it's not able to consume those packets, which means the packet gets queued and it gets dropped. So if you want to remediate this problem, you basically have to solve the CPU issue, which is to solve the ready time. In this case, the ready time was caused by max limited. Basically, we put a cap on the maximum CPU resource the VM can consume, and therefore it was accumulating ready time. Okay, so next I'm going to focus on the disk counters. This is something a lot of people have questions and a little bit of confusion, so I'm going to explain how the counters work here. So this is your entire stack. You have application, guest OS, virtual machine monitor, the vSCSI layer, the ESX storage stack, and then you have a driver. It could be a fiber channel driver, your iSCSI driver, and then you have your HBA. And then you have the fabric, which basically connects your HBA to your array. And array, I only mentioned the array storage processor. So there are multiple latencies here. One is latencies as measured by the guest OS applications, like IOStat, perfmon. That's an application. That's a latency that the application sees. And then there is latency which is measured at the virtual machine monitor level, which is we call as the G average, because that's a latency that will be seen by the guest OS. Now, I just want to highlight here, this latency will be pretty close to the latency as observed by the guest OS, but they may not exactly be the same, because this is a latency that we noticed when we pass the I/O to the guest. Now, guest might queue the I/O, and guest might take some time to consume those I/Os. So there could be some discrepancies between what IOS perfmon sees and what the G average you notice in esxtop. And then there is something called D average, which basically is the latency for the device. So device in this context means LUN. So this is an end-to-end latency that you see from the ESX storage stack to the actual end LUN. Now this is the most important latency of all, because most of the time your storage problem happens because of some configuration issue in your storage setup, which is your fabric, your storage array, or it could be the LUN itself. You could have congestion in the LUN. All of that latency is captured in D average. The remaining average is the K average, which is the time spent in the ESX kernel storage stack. That's why it's called K average. So K average is basically a subtraction of G average with the D average. The K average can be broken down into a subcomponent called as Q average, which basically says that within the kernel, most of the time, my latency was accumulated because I was queuing. And queuing can happen for a number of reasons. I'm going to talk about that in the next slide. So for all practical purposes, the time spent in the storage stack is really, really minimal. And any latency that you see in the K average should be predominantly because of queuing activity. The stack itself consumes like a few hundred microseconds. It doesn't consume in the order of milliseconds. So if you see latency in the order of milliseconds in the K average, it's most likely because you have queuing going on. In a well-configured system, you should not have any queuing happening. You shouldn't have any latency because of queuing. So the Q average should be 0. So that's something you should aim for when you configure your system. So let's talk about this disk I/O queuing. There is queuing which can happen in the guest, which I'm going to call it as guest queue length. there is queuing in the ESX, and there are three types of queuing. One is called AQLN, WQLN, and DQLN. So A stands for adapter, W stands for world, and D stands for device. World means we can have queuing because we can put a cap saying this particular VM can only issue so much IOs. If it exceeds that IO, we'll put a cap. So that is the queue which is defined by WQLN. AQLN means that a particular adapter cannot have more than so many outstanding IOs. So that's a cap for an entire adapter, not for a particular VM. And DQLN is basically a cap for a particular LUN. So you can say this LUN at the maximum can have only so much of outstanding IOs. And then, of course, every array also has a queue length in the array storage port, which is SQLN. So out of all these queue lengths, these three queue lengths are reported in esxtop because they are specific to ESX. Guest queue length is we don't have visibility into it. We don't have visibility into what the array queue length is. And I want to just point out one thing, which is the queue length can change dynamically when you have storage or your control feature enabled, because that's how we throttle the IOs. We change the queue length and we throttle the IOs so that you don't have a LUN being contended by a different host causing performance issue. Okay, that's another nice equation that I want to point out, which is the maximum IOPS that you could achieve is basically the maximum outstanding IOs divided by the average latency that you notice. So to give you an example, if your queue depth is 64 and your average latency, IO latency is 4 milliseconds, then the theoretical max IOPS that you can achieve is 16,000. So that's a very simple. It's a basically queuing theory principle to find out what's the maximum IOPS you can achieve. So this equation, what it tells you is that if you want to increase your IOPS, if you have a database workload and you want to improve your performance of your database workload because it's IO hungry, either you should increase your queue depth or you should try to decrease your latency, disk latency, or you can do a combination of both. Okay, how do you identify queue bottlenecks? So in this case, DQ length specifies the queue length of your LUN. Now this is modifiable by a driver parameter. We have KB articles for it. Basically, you can set a config option to say every LUN on my host will have a queue depth of certain values. If you notice in the screenshot, some LUNs have a queue depth of 1. And those are basically things like your USB drives or ID drives. They don't have a queue length more than 1. So that's why it shows as 1, and they cannot be modified. And some of them have 64. Those are SAN LUNs. Some of them have 32. I think they are for local SCSI disks. This counter, active, basically tells you how many I/O commands are in flight at any point in time. And queued commands tells you how much of the IOs are not being issued yet. So active means they are issued and you're waiting for a response to come back. Queued means you haven't even issued those IOs yet because you're waiting for the queue to clear up. And then there's a thing called world queue, which I mentioned. It's a cap per particular VM. We can set a cap. So that also you can get it by expanding the LUN. When you expand the LUN, we also show what are the VMs are accessing those LUNs. So that is what this shows here, and the world ID of those VMs are shown here. And we also show the queue length of the individual worlds. And this is actually modifiable by an advanced parameter called as num request outstanding. So there's also a KB article on this topic. Okay, so this is an example where the queue is full. Here you see the kernel average is not 0, which I said is not good, which means there is some queuing going on. And if you see all the queuing activity, all the kernel average is attributed to queuing, which is the most likely the case. I would say like 99.9999% that will be the case. The LUN queue depth in this case is 32. And you have 32 IOs in flight and 32 being queued. So what happened in this case is I was sending 64 outstanding IOs at a point in time. I was sending 64 IOs at one shot and was waiting for the response to come back. But we have a queue depth maximum for a LUN, which is 32. So we'll only send 32 IOs and wait for the response to come back before sending the remaining 32. So the remaining 32 got queued. And when it's queued, you're basically waiting. IO never got issued, and therefore the latency goes up. So that was the reason. So to solve this problem in this case, you just have to bump up your queue depth to 64. There's another queue length which I mentioned, which is adapter queue length, which is a cumulative queue for the entire adapter. Now, it's very rare that you will hit a limit on this one, because basically you have to have a lot of LUNs which are accessed through a single adapter, and you have to have outstanding IOs on all the LUNs, and then you're exceeding the queue of the adapter. So the adapter itself have different queue depths based on the type of the adapter. If it's a QLogic adapter, it's 2176 here. iSCSI adapters are 1024. So by looking at the screen itself, I can actually tell which devices are which device by knowing the queue lengths. So you can also expand on the adapter. When you expand the adapter, we also show the paths for the adapter, every path that adapter provides, which means access to every LUN. So in this case, adapter queue can come into play only if you have a system where you're saturating all the LUNs, sending outstanding IOs to all the LUN in such a way that you're exceeding this limit of 2176. So which means in this case, theoretically, you should have, like, let's say 64 LUNs with 64 queue depth, and you should send IOs to all of them simultaneously. So this is very unlikely to happen, but I just want to highlight it that this could happen if you're a heavy IO user in your environment. Okay, so with that, I just want to point out a few takeaways. esxtop is really great for troubleshooting a diverse set of problems. You can solve CPU problems, memory problems, you can find whether you have NFS connectivity issues, you can find all sorts of issues. You can also do root cause analysis by looking at statistics from different screens, from different counters. We can actually correlate, and you can come to a sense what is actually happening in the system. But the key here is you should have a good understanding of the counters. If you really don't understand the counters, they are just a bunch of numbers. You're not going to get anything out of it. And I think one of the things I want to point out is a lot of people try to use esxtop as a one-stop solution for everything, like performance management, alerting, trending, capacity planning. But the reality is the tool is not designed for that. The tool is purely designed for live hotspot troubleshooting. We have been working on a bunch of tools for other use cases. I just want to point it out so that for folks who are interested in those tools, you should definitely check out other talks on that topic. With that, thank you for your time, and I'm willing to take questions.